Welcome to Programming Fluency. This is section 7.1, defining and using structs. So far, each variable you have made holds a single value. In this video, you will learn how to group related values into one unit called a struct. Let's begin. So far, every variable you have made holds one single value, one int, one double, one character, but real things are not single values. A student has a name, an ID number, and a grade point average all at once. A point on a screen has an X and a Y. Let's learn how to bundle several related values into one unit using a struct. This is the plan for this video. First, why we group data together. Keeping related values in separate arrays is fragile and error-prone, and a struct fixes that. Next, defining a struct and the dot operator. You build a blueprint for your data, then read and write its fields with a period. Then, a struct in memory. It is a labeled box of compartments, and we will see the padding the compiler adds for speed. After that, nesting, arrays, and functions. Structs inside structs, arrays of records, and passing a struct to a function. Finally, two common bugs: assigning a string the wrong way and comparing structs the wrong way. Let's start with the problem. Suppose you are tracking 100 students. Each has a name, an ID number, and a grade point average. With the tools you have now, you would need 3 separate arrays: one for names, one for IDs, and one for GPAs. But there's a problem. The data for one student is spread across 3 places: names at I, IDs at I, and GPAs at I. These arrays must always stay in sync. Sort by GPA, and you must rearrange all 3 together. Miss one, and the data is silently wrong. The solution is the struct. A struct groups related variables of different types into a single unit. Each variable inside is called a field or a member. And here is a key point. A struct definition creates a type, a blueprint. It does not create a variable yet. Look at the code. We write the keyword struct, then a name, student, then the fields inside braces, a character array called name, an int called id, and a double called GPA. Notice the semicolon after the closing brace. It is required, and forgetting it is a very common beginner error. Once the type exists, you declare a variable of that type, and you reach into each field with the dot operator, a period. Look at the code. We define a struct point with 2 double fields, x and y, inside main. Struct point p creates a variable named p, then p.x equals 3 sets the x field, and p.y equals 4 sets the y field. Finally, we print them. The output is the point 3, 4. Now the important idea. Each field access, like p.x, behaves exactly like an ordinary double. You can read it, assign to it, and use it in math. The dot just tells C which compartment of the box you want. You do not have to set fields one at a time. You can fill them all at once with braces, just like arrays. Struct student Bob equals, in braces, the string Bob Martinez, then 1002, then 3.42. The values match the fields in declaration order. The first goes to name, the second to id, the third to GPA. There is also a clearer style, called designated initializers. You name each field with a dot, like dot name equals, dot GPA equals, dot id equals. Now the order does not matter because each value is labeled. And here is a handy rule. Any field you leave out is 0 initialized. Writing struct student empty equals braces 0 sets every field to 0. Think of a struct as a labeled box with compartments. Each compartment is one field, and the whole box sits in one contiguous block of memory. This figure shows the layout for a struct with a char, an int, and a double, stored in the order you declared them. The fields sit in one contiguous block, in declaration order. But look closely. After the 1-byte char, the compiler inserts 3 padding bytes before the int. This padding lets the int start at an address divisible by 4, and the double at an address divisible by 8, which the CPU reads faster. So the size of the struct can be larger than the sum of its fields. 1 plus 4 plus 8 is 13, but this struct is actually 16 bytes. Now the definition. Padding is empty bytes the compiler inserts between fields, and sometimes after the last field too, so each one starts at an address its type requires. That trailing padding keeps every element aligned when you have an array of these structs. Now a nice surprise. Unlike arrays, structs can be copied with a single equal sign. In the code, P1 is the point 3, 4. Then P2 equals P1 copies every field from P1 into P2. Next we change P2.x to 99. The output shows P1 is still 3, 4, and P2 is now 99, 4. So P2 equals P1 makes an independent copy. Changing P2 never touches P1. Remember, you cannot write array 2 equals array 1 in C. Array assignment does not work that way. But structs do support direct assignment, copying the whole struct field by field. A struct field can itself be a struct. This lets you build hierarchical data. In the code, we define struct point with x and y, then struct rectangle holds 2 points, one called top left and one called bottom right. Rectangle does not repeat x and y, it reuses point. We initialize box with braces inside braces. The outer braces are for the rectangle and each inner pair is 1 point. To get the width, we chain 2 dots. Box.bottomright.x minus box.topleft.x. Read box.topleft.x from left to right. Start with box, the rectangle. Go to its top left field, which is a point. Then go to that point's x field. Each dot steps you 1 level deeper into the box. Now we can solve the problem we started with. Instead of 3 parallel arrays, we make one array of structs. Struct student roster of 3, initialized with 3 inner brace groups, 1 per student. Each group holds a name, an ID, and a GPA bundled together. To print them, we loop over the array. Roster at I selects the struct for 1 student. Then .name, .id, and .gpa select the fields inside. This is why it beats parallel arrays. Each student's data travels together as one unit. Sort the array by GPA, and the name, ID, and GPA always stay matched. They can never drift out of sync. You can pass a struct to a function just like any other value. The function receives a copy of the entire struct. This is the same pass-by-value rule you learned for ints. Distance squared takes a struct point p and returns p.x times p.x plus p.y times p.y. In main, we pass target the point 3, 4. The result is 9 plus 16, which is 25. Because the function got a copy, changing p inside would not affect the caller's variable. A function can also return a struct. The value is copied back to the caller, which is always safe. But passing a big struct by value copies every byte, every call. For a small point, that is fine. For a large struct, it is wasteful, and the next section fixes that with pointers. Now 2 common bugs. The first involves strings. You write struct student s, Then s.name equals the string Alice, expecting it to store the name. Instead, the compiler rejects it with assignment to expression with array type. Why? The name field is a char array, and you cannot assign to an array with equals after it is declared. This is the same rule you met with strings. The fix is to copy the characters, using strcpy from string.age, or set the name in the initializer braces when you first create the struct. The second bug is comparing structs with the equals operator. You have 2 points, p1 and p2, both holding 1, 2. You write if p1 equals p2, expecting true. But the compiler rejects it, with invalid operands to binary equals. C does not define equals for structs. Part of the reason is padding. Those hidden padding bytes can hold anything, so a raw byte comparison could be wrong. The fix is to compare the fields yourself, one at a time. If p1.x equals p2.x and p1.y equals p2.y. Let's recap. A struct groups related variables of different types into one named unit. You define a struct type with the struct keyword, a tag, the fields in braces, and a semicolon. Do not forget that semicolon. You access fields with the dot operator, and you initialize with braces or with clearer designated initializers. In memory, the fields sit contiguously, with padding for alignment, so the size may be larger than you expect. Structs are flexible. You can assign one with equals, nest one inside another, store them in arrays, and pass them to functions by value. And watch 2 traps. Do not assign a string with equals, use strcpy. And do not compare structs with equals, compare field by field. Next, we pass a big struct by pointer and meet the arrow operator.